quick summary, you recognize these guys? They are the spherical coordinates conversions from x, y, z to rho, phi, and theta. You're basically going to be doing questions involving a sphere or a sphere interacting with a cone. And what I want to do is basically just go through the setting up, give you hints how to do the homework questions. So in this question, we're being asked to find this triple integral, and E is described as being the points inside a sphere of radius 4. That's essentially what that is. And that the y coordinates are greater than or equal to 0. And so that's the key one that we have to take care of, right? So if the y coordinates are going to be positive, aren't we talking about that part of the world? You agree? And I'm just put that in the wrong direction, my apologies. You're agreeing with me, but the y is being positive, right? Or there we go, there we go. I'm useless at drawing 3D. Would you agree there? It's that side. That's what I was trying to draw the first time, and yours is good. So bearing that in mind, but everything else is pretty much a sphere. Are you happy about the 0 to 4 because the radius is 4? So rho goes from 0 to 4. Cool with that. Now, how do you describe essentially a hemisphere, right? That's the right-hand side. Well, the values that are going to be important here are actually not going to be the phi guys. They're still going to be 0 to pi. And
phi was 0 to pi as when you're dealing with the hemisphere.
I can't hear you, Sally. If you could say it again, please.
I thought that phi was 0 to pi halves when you were dealing with the hemisphere.
It's 0 to pi. Oh, you know, yes, it is pi halves if the hemisphere was up here. But depends on which hemisphere you're talking about, right? So in this case, it's, for want of a better word, if you take a sphere, we're taking the right-hand side, right? If you take a sphere, you could take the top half side. So the top half side, you would be right. But for this one, what is the guy? Well, it's going to be the thetas. Now, if you look at this shape vertically above, right, what you would see, got to get my orientation right. Actually, I was right the first time. It was that shape. You'd see that. And that takes theta from 0 to pi. That was the bottom line. So if you want y to be greater than or equal to 0, you're talking about the right-hand side of a sphere. But if you just look at the x and y axis, can you see the y-axis is positive, but the x goes from here to here? And so that basically reduces us to here. Now, why is it 0 to pi? Right, the phi starts up there, that's 0, and it finishes down here, which is pi, which is exactly what you'd expect. So when you're setting this thing up, you basically, in any order you like, you can go 0 to pi, 0 to pi, and rho goes from 0 to 4, and then y squared becomes that guy squared, and you have to remember to stick in the rho squared sine phi stuff, which I've actually got already written. So the majority of what I want to do today is take the question and figure out what the range of these guys are based on the shape that you've got. So this one was for a hemisphere, but the right-hand side, and that meant that this was the one that we changed. Next one in our list is going to be question 7. And question 7, it's a sphere and it's in the first octant. The first octant would be a guy here. There's no way I'm going to even try and draw that. Can you imagine you've got a one piece of a sphere, and it's the one piece that's in the plus X, Y, and Z world, right? So the radius is 1. That is good. What will be the range of phi? Phi starts here at 0 and then it curves all the way down. What would be the range of phi if you were only doing that piece of the sphere that's here? Start at 0.
0 to pi over 2.
Pi over 2. Now, be very careful. The theta, right, when you're in the first quadrant, or first octant, I should say, which will now be the first quadrant because we're looking at it on the ground. 0 to what? If you're in the first octant, what is the range of theta?
Wouldn't it also be 0 to pi halves?
Well, there's 0. There's pi halves. Agreed? Are we good with that question? Right now, I haven't written down what the integral is. It really doesn't matter because isn't the rest kind of flows from once you got these right, you turn any x's and y's using this, and you turn the dv into this, and you're probably going to be able to do variable separable. I'm sure you will. Nine now. You're being asked to find the volume of a shape, a solid, made from a ball, which I don't know why they don't call it a sphere, but call it what you like. A sphere where rho is less than or equal to some number, but the number is going to be called A, and it's between a cone, and let me check if that's the way they phrase it, because that's the answer, but is that how they phrase it? Yeah, the cone is between those two guys. Well, if you tell me that, you've really gave this guy away. You agree? If you tell me the cone is this guy to that guy, you know the five fellas, small to big. Right, if it is a sphere, which they are calling a ball, and its radius is everybody less than or equal to A, isn't that 0 to A? And since it's the entire sphere, isn't that 0 to 2 pi? Are you comfortable with the volume of a ball lying between these two cones? The two cones give you this, the phi guys. The fact it's an entire sphere or a ball is 0 to A because rho is that number, and the whole thing is 0 to 2 pi. And so when you plug this all in, you're going to have theta from 0 to 2 pi. Phi is going to be pi upon 6 to pi upon 3. And rho is going to be 0 to A of this guy. Oh, wait a minute. Shouldn't there be a function here? Well, it's hidden in this. You want to find the volume of something. If you want to find the volume of something, what triple integral do you always find? The triple integral of what gets your volume?
1.
That's technically there's a 1 there, which you probably won't write. So that's the integral. I'm sure they're variable separable, and that's how you would tackle question 9. So what I'm doing is I'm going through most of these questions, as I said, and we're going to focus on that, because once that's done, it's pretty much the hard part's over. Next one. This guy. Now, this region is described as find the volume. Well, that's easy, so that's where the 1's going to come from. And what's it made from? It's made from a sphere that looks like this. So what's that, radius at 8. And above the XY plane,
Is that a 64?
Yes. And the radius then is 8. And it's to be below that cone. Oh, by the way, when you do a cone, right, what's the range of values you get when you talk about a cone? From 0 to pi upon 2, wouldn't that generate a cone? Right, essentially. And theta is always 0 to 2 pi, so I don't worry about what the thetas of the rows are doing. That would be a cone where you'd start with one answer and you get another. But in this case, it's, we have to get two things factored in here. Right, you got a sphere and it's above the XY plane. So that's 0 to 8. Because isn't the radius still 0 to 8 no matter how much of a sphere you use? That's not going to get changed. Now, what does this phi become? Oh, let's do the theta. It's a whole circle, even although it's only the top half. If I could draw this thing, which I can't. Can you imagine it looks something like that, right? So it's the top half. So theta is still 0 to 2 pi. The only fella that we've got to worry about are how these two things work, right? Now, if it was a whole sphere, when you go there, but what's this fella is going to be above the XY plane, and the guy you're going to get here is pi upon 4. And that's the limits, and you're going to plug them in and get your answer. I'll leave that one there for a minute. Oh, we've got that guy. I don't want to do that until later. Let's focus on a different type of question. There's two like this. I think it's 13 and 14. I take it back. It is 13. Is it a 14? No, they're just one of them. Okay. Can you hear that in the background? It's distracting. If you're wondering what it is, I don't have a medical complaint. My puppy has got the squeaky pig, and every time you squeeze it or bite it, she's having great fun. So in this question, x equals 0 to x equals 10, y equals 0 to 100 take away x squared, and z equals, try to write this all down, x squared plus y squared, and over here is going to be 200 take away x squared take away y squared. A bit strange, but that's fine. Okay, we are ready to go. Oh, and we have a function here, x, y, dz, dy, dx. Now, if you try to integrate that guy with these x, y's, and z's, you would have major algebraic problems. I'm not even sure it's doable, because what the question wants us to do is to convert this into spherical coordinates. Okay, so if I tell you that z is equal to 200 take away x squared take away y squared, can I cut some corners and say that eventually it becomes that? Would you agree? If you square both sides and move things around. Do you recognize that as the sphere that we were always expecting to get? Agreed? What's the radius of this sphere?
Square root of 200.
Which you can call 10 root 2. Agreed? Right. So I already know who rho is. Now, there isn't anything remarkable going on here directly until we get to the y guys. So let's see what happens here. Y equals this fella. And if I rearrange this, don't I get x squared plus y squared equals 10? Great. Now, if I draw that.
Would it be x squared plus y squared equals 100?
Yes, sorry. Which is a circle of radius 10. Great. But when you factor in that the x value goes from 0 to 10, doesn't this now just become that guy? So if you want to find out what this fella looks like, basically we just need to say, I can see that won't theta go from where to where? How would you, what values of theta would generate half a circle that looks like this?
Leave pi over 2 to pi over 2.
Oh, you're doing it positive, aren't you?
Yeah.
Yeah, it's probably less. Can we just change your answer a little bit?
Okay.
I know what you said is right, but if you did it the way you said it, you probably make the answer negative because the big guy comes before the little guy and that nonsense, right? Are we cool with that? Okay, who's missing? We don't know yet who phi is going to be. Well, I'm looking at, I've got their solution here and I'm trying to figure out where I can see what they've got, but I can't see why they got it. Let's see. Now I got my theas right and I got my other guys right. I'll write down what they have, but I'm not 100% sure why that's happening. I guess if you take that and you use it in here, then aren't you saying that Z, this is square root of 100, so you're saying Z is 10. No. Okay. Hold off on, this is the answer. But there's nothing obvious that I can see why that is the answer. Is there a restriction here that I've not taken into account? That's definitely a sphere. That came from that, that's not an issue. That's definitely a circle, right? But we're only looking at, well, when you put those two together, at least you're looking at this side. Oh. So I can see the 0. What I can't see is why that is pi upon 4. I'm thinking of you taking the Z and you just dropping it down. That should be pi upon 2, you would think. Okay.
Isn't this information telling us that essentially y is always 0?
Well, up here you're told that y is this to that. So, oh, y is 0. Oh, y is 0. Now I got the answer. They only use that piece of the guy. And that piece of the guy would get you pi upon 4. Okay, I'm happy.
And and then why wouldn't that make a theta 0 to pi over 2?
It should. And it does. Right. Okay. So y equals 0 to there and x equals 0 to 10 generates that little quarter. And that little quarter is why I have 0 to pi upon 2, right? That makes sense now. And the phi, well, you're coming up and you're meeting up with this guy. And that's half of what the shape is. You're not going all the way down. Half of pi upon 2, pi upon 4. Yeah. In my brain, that makes sense. Cool. Okay, that one there. That is, who's left? I think it's question 12. Ah, I knew why I kept this one last. Our last question is finding that guy. You remember your test question, how long those blinking things are? We are going to do a center of mass for a shape that is basically a sphere interacting with a cone. So we are going to be looking for the center of mass of a sphere with a cone. Oh, we had the shape like this before. Haven't they borne a cone hole into a sphere, essentially? And we're looking for the mass of that. So first thing I'm going to do is tell you something that's going to make your life a lot easier. Why can I say X bar and Y bar are both 0 in this combination? I can't say Z is 0 because it's not, but I can definitely say that the center is going to be for X and Y are both going to be 0. Where's that coming from?
Oh, would it be because when one of them is sines, when you integrate, you'll get cosines, and then you'll get something like 1 minus 1, which is 0. But when you're integrating with the cosine, you'll get a sine, which would be just 0.
But you're just doing it by figuring out what the calculations would look like, and what you're saying is correct. I'm going to do it a lot easier than that. I'm just going to say symmetry. If it was just a sphere of any radius, wouldn't the center of mass be the origin? 0, 0, 0. If you introduce a cone, isn't the cone only going to affect the Z value? Because the X and Y still have the symmetry. So you're going to keep the 0 and 0. So that means we only need to find one guy, Z bar. So it's a little bit less work than it would be, right? So if you are doing spherical coordinates and you know it's a sphere there, the chances are 2 of the 3 things are going to be zeros, right? In this case, X and Y are most likely. So far, so good. Now,
Fun thing is this puts the center of mass outside the volume of the object.
I haven't calculated it. You can have that. You can have centers of mass outside shapes. Tends to make them kind of unstable, doesn't it? Tend to make them want to fall over or something bad happen. But yeah, you could have it. Have you looked at the number to see what it is?
Well, no, it's just if X and Y are 0, and you're talking about a cone that has interacted with a sphere. If the apex of
I gotcha. Yes, the center of mass is going to be inside the hole, isn't it? That the cone has generated. Yeah, that makes perfect sense. It would be, wouldn't it? I don't think that's a bad place to have it. I mean, for stability, it's probably not too bad a place. So what do we need to do? Well, technically, we need to find the mass of this shape. They're not telling you the density function, so we'll assume that it's 1. So the mass is going to be the same thing as the volume. So we're going to do a triple integral over E 1 dV. That's what it would look like in XY world. Let's set up the limits of integration in terms of these 3 variables. Rho is going to be 0 to 8. Are you happy with that? 0 to 8. This guy is a cone, and we're going to go from 0 to pi upon 4 again. And what we're going to do for theta, well, it's going to be the whole circle. So it's pretty much pretty nice.
Is it pi fourths or pi halves?
Pi fourths. Now, the triple integral then is going to be from 0 to 2 pi, from 0 to pi upon 4, and from 0 to 8 of 1. But I have to factor in, where is our little guy? That guy. So it's a rho squared, a sine phi, a d rho, And since I don't have room, I'll just call it TV for the time being. So I should be able to separate these out from 0 to 2 pi of 1, from phi equals 0 to pi upon 4 of the sine of phi, and from rho equals 0 to 8 for rho squared. Okay. Are you comfortable with the separation here? This triple integral with that guy. I'll do a theta with this fella. The phi can have the sine phi with it, and the rho gets you that. This guy is 2 pi. This guy is root 2 over 2 when you're finished. And this guy is, yikes, this guy is a third rho cubed. So it's 1/3 of 8 cubed. What on earth is 8 cubed? It should be 256, I think.
It's 512.
512. So 512 thirds. So I put that horrible mass together. What do I get? I get a root 2, a pi, a 512 over 3. Okay, let me check the answer in that. No, they don't get that. 0 to pi upon 4 is good. Oh, that's not the answer. Okay, I'm cool. I'm cool. This is not right. They say 0. Can anybody see anything wrong with this? Because I am not getting, I only get the answer here that I'm looking at right now. And they say it's 512 thirds pi, which I like. But they don't have this guy. They have 2 take away this guy. Oh, of course, it's a blinking cosine when you
Negative
integrate
cosine.
it. Yeah. Okay. This fella here is that. Okay. I'm glad I checked the answer. So it's going to be eventually 512 over 3, which is this guy, a pi, and this guy and this guy, and you multiply it and cancel it out, you end up with 2 take away square root of 2. So if you multiply this by that, you get that. So that we do agree on. That's good. Now the only one that we're missing, because where's my guy? The only one we're missing is Z. That means we have to find that fella. So it's going to be the same triple integral as before. 0 to 2 pi, phi equals 0 to pi upon 4, and rho equals 0 to 8, right? It's going to be that guy. With, well, if it's xy, it's z times rho squared sine phi d rho d phi d theta. And the z gets turned into this fella. So it's 0 to 2 pi, 0 to pi over 4, 0 to 8. A rho cosine times this guy, that gets me a rho cubed, a sine phi, cosine of phi. I'll do a rho, I'll do a phi, and I'll do a theta. So I'm going to have theta equals 0 to 2 pi of 1. I'm going to go phi equals 0 to pi upon 4 of sine cosine. And then I'm going to do rho equals 0 to rho equals 8 of rho cubed d rho. And you're going to just trust me here because I don't want to spend too much time. But according to the answer I've got there, you get 512 pi, which means that z bar is the moment xy divided by the mass. So it's 512 pi divided by 512 thirds pi to take away that guy. And that'll cancel with that. That'll cancel with that. And you'll get a 3 on the top. Okay. We agree with the answer. So where would that be? If I do that as a decimal, it'd be 3 divided by 2, take away the square root of 2. Ooh. So it would be in the z-axis, it would be about here, if you think that's 5. What's the sphere? It's 8, so the sphere gets up to here. So imagine you have a sphere, and then you're cutting a cone out of it. Yeah. It makes sense. Wouldn't it be slightly higher above? It wouldn't be 4, which is the middle. Wouldn't it be a higher than that? Because isn't there more material higher up and less material lower down because of the way the hole has been cut, right? You've got the sphere cutting into it. So, I mean, 4 is the middle, right? That would be kind of the center. 5. Okay. In my mind, that makes sense. It would be in a hole inside that cone. Whew, new guy. A little bit rushed there, but I wanted to get enough time to get this started and so we can finish it tomorrow. I'll take more time now. Just it loads up. We are going to do section 15.9, change of variables. The closest you could come to what this is like is u-subs. Aren't u-subs change of variables? Where you have an integral in x's and y's, because we're going to start with integrals, double integrals again, first, in terms of x's and y's, and you change the variable and find a different integral that's equal to it. So the analogy might be if I gave you that integral to do, who cares, from 0 to 2 or something, right? Would you agree that you would do a change in variable? You would do what we call a u-sub. And the u-sub in this case would probably be 2x squared plus 1. That seem reasonable? But when you do double integrals, how do they work? Well, imagine that you had y equals the square root of 4 take away x squared with a minus on it, and y equals plus the square root of 4 take away x squared. And the x went from, say, 0 to 2. Now, if I, don't really matter what's here, but let's say it was xy, and you had to do a dx, be a y first, a dy dx. Now, if I gave you that integral to do, just looking at it, what would you probably use for that double integral? Because we have done ones like that. What would we use? What coordinate system would we use to do that?
Wouldn't we want to use polar?
Yes, we would, right? So if you take this guy, you're basically getting a circle that looks like this, but you're only using x from 0 to 2. So if you draw that shape, it's a circle, but only using x from 0 to 2, right? And from that, couldn't you then set up your usual limits of integration and polar? So how would that work in this situation? Well, don't you do x equals r cos theta and y equals r sin theta? Right? And change in variable of a double, right? Say some region E, so that would be E, of your function, dv. Well, it would become a new region. Well, it's basically the same region, but described in a different way. Instead of x's and y's, you would do r cos theta, r sin theta. And instead of the dv, wouldn't you do r, dr, d theta? Remember the polar? Remember polar? Where on earth did that come from? Remember we said it's there, you got to live with it? Let's show you where it comes from. The formula, we'll just call it that. And we'll call it dv dashed. Let's do a change in variable. dv dashed is the Jacobian, it's the name we give to this guy, with a new fella attached. So if you want to do, oh, I'll do it here. If you want to do x as r cos theta, and you want to do y as r sin theta, that's going to be your change in variable, right? Then you can do dx. The Jacobian is in general described like this. You go dx, d theta, dy, put the answers are. Then you do dx by d theta, dy by d theta. The Jacobian is, it's like a partial derivative with two different variables, and you do every permutation. So you do the derivative of x with respect to r, the derivative of y with respect to r, then x with respect to theta and y with respect to theta. And those two vertical lines are not just cosmetic. Any of you done 2 by 2 matrices and had to find the determinant of them? That's what that is. So let's put the pieces in. If you differentiate this with respect to r, you get cosine theta. If you differentiate this with respect to r, you get sin theta. If you differentiate this with respect to theta, you get negative r sin theta. And if you differentiate this with respect to theta, you get r cosine theta. Are you happy about these 4 guys or these 4 guys? Now, a 2 by 2 matrix, the determinant of it is those 2 guys, which are called the major diagonal, take away those 2 guys. So what do you get? You get r cos squared theta, take away negative r sine squared theta, so you get plus r sine squared theta. And this fella can pull out an r as a common factor. And do you see that you get left with r? So when I do this fella, can you see that's basically the dv dies, right? And that's the Jacobian piece. So we can actually change variables by finding the Jacobian and then doing it in terms of whatever these are, r and theta. So let's make up our own pretend coordinate system. So I've decided that in my coordinate system, you tell me how things are, because the x coordinate is going to be sine theta, and the y coordinate is going to be r squared cos theta. So I can tell you right now, in my particular universe, the x coordinates only take values from -1 to 1. Can you see, because of that restriction? And can't the y values be almost anything, right? So this would be a weird world, but it would essentially be, wouldn't it be a world where the x's lived in that region, right? What would the Jacobian look like? Well, the Jacobian in this world would be the derivative with respect to r for x and y, and the derivative with respect to theta of x and y. If you differentiate this guy, you get cosine theta. Oh, wait a minute. If you differentiate this guy with respect to r, don't you just get 0? And if you differentiate this guy with respect to r, you get 2r cos theta. If you differentiate this guy with respect to theta, now you get the cosine theta. And if you differentiate this guy, you get negative r squared sine theta. If you now do the major, take away the minor, you will get 2r cos squared theta, right? And 0, I should say, take away that. So the answer is negative 2r cos squared theta. So if I had a region E and some function in terms of x and y, and I wanted to do it in terms of x and y, but it wasn't going to work for me, couldn't I rearrange it and just do it in terms of r and theta? The Jacobian, oh, by the way, the Jacobian, almost forgot, is always positive. So if your answer happens to be negative, make it positive. Right, now I can do it. There is 2r cos squared theta, and then I can do a dr d theta. So do you see my new world? I'm essentially changing my coordinate system to suit the integration. There is another guy that I won't show you because it takes too long to prove. I'm trying to find the page. Remember that guy from spherical, for instance? So in spherical, you have rho squared sine phi d rho d phi d theta. And these are the guys, these are your, essentially your transformations. This is a three-dimensional one. When you do a three-dimensional one, you do an x, y, z with, what's the order we're doing? A rho, phi, theta. And this gets messy. It's this guy with respect to rho, this guy with respect to rho, this guy with respect to rho. Then you do the y's with respect to phi, the x, the y, and the z with respect to phi. And then you finish with thetas. So you do x with theta, y with theta, and z with theta. Now, if you've done math one, it's 252, isn't it, linear algebra? Do you remember finding the determinant of a 3x3 matrix? Can you trust me that that guy ends up simplifying to him? So that's why spherical coordinates have that little extra guy. which means, Brendan, if you come up with a new coordinate system, right, a way of telling me where something is in 3D space that works really well, right? In other words, gives you a nice simple Jacobian and also would be practical, you know, so it could get used a lot, then you can call it the Brendan coordinate system.
All right,
Terence,
sounds good.
don't hold your hopes out. We basically think we've got all the good ones already found. But here you can prove me wrong. Terence, what's your question?
Okay, I've seen a 2x2.
Okay, you've seen a 2x2. I guess we lost the audio. He went. You'd have to look up. We're not going to do 3x3, so we don't need to worry about it, right? But we could do 2x2s. Oh, he's back again, so we'll get the end of his question. While we're waiting for that, will you say your last name and we'll get ready to bye-bye in a moment. Hi, Terence, what was your question? You've seen 2x2s, that much I caught before you disappeared.
Yeah, so where can I go for how to do a 3x3?
You can look it up under linear algebra, but basically you use this guy and that determinant, then you use this guy and that 2x2 determinant, and then finally, so I'll have to go 3 now, you use that guy and those 2x2, and it's this fella times that 2x2 there, so it would be dy d that's too big to write, I don't have time, but basically that guy times 2x2 determinant, take away this guy times that 2x2 determinant, and then lastly plus this guy times this 2x2 determinant. So you find it's a big ugly mess, isn't it? But it's much easier to do when you've actually got numbers and things. But you can look it up. It's determinant of a 3x3 matrix. If it's equal to 0, just came to me. If it's equal to 0, why is that bad news? Your 3x3, right? Your Jacobian ends up being the number 0. Why would that be bad news? I'll phrase it a different way. Could you use that particular transformation? Would it give you an answer that you could work with?
No.
Because won't all your answers be 0? Right. So what does that probably mean? It means you've created a coordinate system that doesn't exist in real life. In other words, you won't be able to tell me where anything is in 3D space. Oh, how about this? X is 1, Y is 2, and Z is 3. Can you imagine that would be a pretty dumb coordinate system? Because you could only tell me where one point was, right? All the other points in the universe couldn't be described by it. And that would get you a Jacobian of 0, for instance. Okay, I'll hang about for questions, but that's us for today.